Let me, right now 30 participants, so attendance is a bit low. Still, I'll start with the theory part. So let me share the screen. I hope the screen is visible. Thank you. This was a program that we created for taking out the how to, what we can say, how to store the variables inside the array. This is basically a simple structure, right? And then we have discussed how the malloc works using a paint diagrams. Now, what is the limitation of this approach? Is that at the start of the program itself, when the program execution starts, immediately we have assigned 10 blocks of memory. Like, so at the start of the program itself, at the beginning, we immediately we get 10 blocks. And so on and up to 10. Right, so we have 10 blocks with us, and right here simply n. Starting with the first block, which will start at index 0. Now it's n is up to you, up to what memory you want to reserve, right? So this much memory block will be reserved despite whether that memory is being used or not. So this is one problem. The very important problem about this approach is you cannot progress in the program if you reach this maximum limit, right? So if you reach this nth limit, whatever you have entered, from that point onwards, your program cannot proceed further. We have to simply print a warning. And in fact, in our programming task, what we have done is we have asked people to enter 10 students object, and we stored these 10 objects inside the array. And if a person selects, or if the user selects this add student menu, if the student selects this add student menu for the next time, like for the 11th time, then you will be printing a message. The message is the limit of how many users can be entered, or the data limit or the array limit has reached, or the max limit of the array is reached, and hence we cannot add furthermore records. So that was the warning message or error message that we have to display. So most of you people have finished with this assignment, and you are already aware about that if we insert 10 records, then no further records can be stored inside the this particular program, right? See, if I create here struct student, let's say store, as it was in problem statement, and if I just pass 10 here, it directly means that I can store only 10 objects of the store. And even if I'm storing only one object, then I'm at the wastage of 9 locations. And if I store all 10 objects and I need to store 11th one, we do not have the storage with us, right? So that is a problem. To overcome this limitation, that the first limitation is we are wasting the memory, and the second limitation is if we need more memory, then it is not possible to allocate it. To overcome this particular limitations, there are functions in the C called as mloc. This is specifically about C language, cloc, right? And there is a function called as free, which will free the memory. Now, what is the importance of these three functions, mloc, cloc, and free? That is a part of today's discussion. We have already started with mloc in the last session, theory part, right? So we will continue with mloc. Then we will see what is the cloc, that is a continuous allocation, and then free. So memory alloc, continuous allocation, calloc, and many people pronounce it as a calloc. So I'll give you the freedom how you want to provide it, pronounce it, whether calloc or calloc, it's up to you. During this time, I've got a what we can say, kind of flexible pronouncing calloc as a calloc or a calloc as and when I want. So I even really do not pay attention. So it's up to you how you want to pronounce it. You will find a mixed feedback. People are calling it as a CLOC or CALOC. Okay, and MLOC, mostly people call it as MLOC. Sometimes people directly use long form also, like memory allocation and continuous allocation. So it's up to you how you want to call these functions. So we are listing three things here: memory alloc, CALOC, and the last thing is free. So we have to understand what really defines when we create a object of 10 similar type of data. In this case, it is student structure, and we are creating 10 arrays of array of size 10. So that is a continuous allocation also. And then why we need this, right? So first thing is vestige of memory. If we are not using them, the memory will be allocated, and you can't proceed further 11, right? So that is a primary reason people have defined something called as memory allocation. So what are the effects of having these functions? That is a very important discussion point. So let's start. Let's understand how things work when we create a particular variable. For that, I'll make use of a blank paint menu. So let's say I have created a variable. Let's keep this program as it is, and let me create a blank new project for the discussion purpose of how the memory has been managed. Let's call that so mem2 is there. So let's say you have created an array of size 5. Okay, say integer arr of size 5. Okay, now simple for loop can be used to initialize it. I is equal to 0, I is less than 5, I plus plus, and what you will write is arr of I is equal to I plus 1. So it's very simple thing. And now I'll use simple for loop again. Int, sorry, I should write here I integer I is equal to 0, I is less than 5, and I plus plus, and again now I'll make use of printf statement to print the output, right? So %d and arr of course the index value, and we would like to print the variables. I'll keep a simple approach. I'll say integer I is equal to 0, initialize it to the 0. Okay, and inside the for loop, I'll be just reusing it again. Now, if I run this program, it is pretty much like any, all of you can predict what will be the output, right? So we are just, we'll see 1, 2, 3, 4, 5 in a continuous line. So V into 3, 4, 5 in a continuous line. Now, what if, now what is the size of the array? Size of the array is 5, right? And after that, I have a variable called as integer I. Okay, so let me create one more variable called as integer k, and I'll initialize this variable to 0. So pay attention closely here what is happening. Okay, it's a very important concept. So what I've called as, even one of the student from your class have posted a question about this, that one of the student have already faced this issue, and I've replied him that it is something called as an overflow problem. So we are discussing memory overflow, and that is another reason that people moved with the memory allocation and continuous allocation functions rather than depending on the static allocation for the program management. So what we have having the setup is very simple. We have integer array of size 5, and then we have integer k is equal to 0, and then we have I variable which we are using to keep the index. And what we will do is we will use the index value as 6, less than 6, while printing. Okay. Now, see, array have only 5 locations, and it's clearly visible from the program that we are actually creating a problem. The problem is that we are trying to use a 6 location, whereas I have only 5 locations with me, and I've literally with intention we are trying to access 6 locations. So obviously this will result in some sort of a malfunctioning in the program, right? This should result in some sort of malfunctioning. Let's see what happens. So it has compiled with 0 errors, and there is one warning, unused variable k. So we'll ignore that. We haven't used k, no problem. Now let me run this. Can you see that 1, 2, 3, 4, 5, 6 is been printed on the screen? Are you with me? So it's a deep question how it happened. Right. So it's clearly an issue. How could a program with the array size of 5 could simply keep 6 locations with it? That's a very, what we can say, it should be triggering a very thought process in your brain that how, okay, what is exactly happening in the background. And this is again one of the reason people mostly extensively use memory allocation rather than assigning a static block while writing the programs. So what I'll do is I'll use another printf statement, printf. Let's try to print the k variable. So look, the k is initialized to 0, k is initialized to 0, and we nowhere in the program we are changing the value of k. We haven't changed k intentionally anywhere. Let me recompile it. Uh, Okay, though what should I do here is, for the sake of clear understanding, I should say k is equal to, and recompile and run. Can you see, guys, k is equal to 6? Can you see it? K is equal to 6. Great. So the problem that we are looking at is called as overflow problem or a stack overflow problem. This particular problem will haunt us when we call functions, and when we pass pointers to a functions, and when we are expecting a returned value from that function, the overflow problem will literally eat our heads, and it will be a very painful process to identify where the exact problem is and then resolving that problem. Because see here, what you will expect from the program or the C environment is that C should complain because you haven't modified the value of k. So if this program has been given as an let's say you are appearing for one of the company's aptitude test, maybe the persistent, the one who really pays a lot of focus on C understanding. Let's say this is the ideal question for the aptitude, right? And as a good programmer, you know that the k is initialized to 0, so it must print 0 because you are not modifying k anywhere, right? But now just we have verified that k has been modified accidentally and it is printing 6, right? So this is the this is the problem with the memory management of C environment, right? So a lot of people complain that C is not safe because you can literally cross the boundaries and work with it. By the way, this effect is not guaranteed. For example, if I put a comment on this, then it is going to create a lot of problem because at the last I plus plus operation, and when you try to store the value, you are actually modifying the index itself. So uh, when I becomes 6, that is a last value 5, you are saying 5 plus 1 6, and again you are modifying the index I itself because there is no sixth place, and you will be writing 6 inside I, So it's a kind of confusing story because the for loop will find it difficult to end, and the value of I will keep on rolling. So it is another problem, right? So why it is happening? Continuous memory allocation. So what we have done is we have reserved 5 blocks. We have reserved 5 blocks for the array. So let's say we have 0, 1, 2, 3. Okay, 0, 1, 2, 3, 4, 5. So 5 blocks of the array, and we are this memory has been starting. This memory is starting with the ARR. Okay, so we have ARR array with which the memory has started, and now we have another variable called as k. So after this fifth location, there is a variable called as k. So this is k. And when you say ARR of 5, okay, 0 and I is less than 6, that means you are starting with the 0th index. You will be modifying 1, 2, 3, 4. And even if there is no fifth index inside the array, as the entire memory is allocated on a continuous memory space, this memory is called as a stack. We will immediately see what is a stack in the second unit, but before that, we will just simply call it as a continuous allocation. So as this memory is a continuous allocation, when you try to modify the fifth index, now you can see that you are actually, when you are saying ARR of 5, you are actually modifying k, right? So that is what is the issue. Stack continuous stack allocation. Okay. Now, it literally means what? That if I need to store, like say, let's replace this ARR concept with the struct student store, and you have created 10 objects. You want to store 10 objects. And let's say there is a k variable. There is a k variable. Then there is a good chance that there is a very good chance that after filing up 10 records of student in the array of store called as store, so we are calling this array as store, right? So after exhausting the limit of store array, there is a good chance that you will accidentally do the same thing that you are doing in the left side scenario, that is ending up overwriting the value of k. And worst part in this case, in the earlier case, the array was of integer type itself. But in this case, the k is of int type and the store is of 10 type. So it will even have a disastrous effect, even more disastrous effect if you overrun in this situation. That's why it was very important to handle this part in the task 3 that we programmed in this week. The task 3, if the user selects add record option after exhausting the limit of the array, then there should be a warning message that you can't store the next record because the array limit is already reached. So it was a very important condition to handle in the program. Now, how come memory allocation function overcomes this? So before understanding memory allocation, one concept should be very clear in our brain. Okay, so for computer, everything is a memory. So every block is similar. So let's assume uh, I hope that I have your people's attention with me. So are you attending? Int I is equal to 0. I didn't get it. Jatin, are you there? Will you please tell me what you wanted to say when I say int I is equal to 0? I've just seen it. Jatin? No. Fine. So let's understand what is really meaning of a memory and how computer sees it and how we can deal with it. So for computer or for C environment, C programming environment, or for any program that we write, memory is just nothing but continuous blocks. Okay, piece of a continuous blocks. We are assuming that, or let's say that this each block is of 1 byte. So this each block size is of 1 byte. That is for understanding purpose. So now when we have computer's memory of 1 byte for the each block, and now we have different data types. Let's create some of the data types. Okay, so I hope you understood this concept. So I'll rather remove this to understand the further part. I'll just, what I'll do is I'll declare a few different data types. So I'll say character C, and we'll store alphabet A inside it. Now what we are having is, I even don't need this printf statement because we just want to understand how the memory works, right? So I'll just keep these three statements. Now with the assumption, now here are few assumptions that we will make. What is the first assumption? First assumption is that I'll assume that the integer takes 2 bytes. So that is assumption because I'm using a 64-bit system. It's not true. It is different. So I'll assume that the int is going to take 2 bytes for the storage. Character will take 1 byte for the storage. Okay, and again there is an int I variable which will again take 2 bytes for the storage. So what will happen is the C program will calculate the total space required for this. So now we can also calculate what is the total space required for this. So int k is the first variable, so I need 2 bytes plus a C character variable needs 1 byte, so I'll say plus 1, and then again integer I, wherein we have, again it's an integer variable, so it will again need 2 bytes. So for compiler, you are simply demanding this much memory. So 2 plus 1, 3 plus 2, 5. So what computer does is, computer says that, okay, this particular program is in the need of 5 bytes. And from the memory chunk available, 1, 2, 3, 4, 5, from the chunk of memory which is available to the system, it will take these 5 bytes and it will allocate it to the program. So this 5 bytes will be allocated to the program. It will go to the, let's say it's called as program 1. Okay, so the program 1 receives 5 bytes. Now you are saying that I will store k as an, I want to store a data in 2 bytes as a bunch of 2 bytes. Then you are saying that the second data is a bunch of 1 byte, and again my third data again is a bunch of 2 bytes. So who is telling it? The programmer is telling to the system that the first 2 bytes from the, so total 5 bytes allocated. From these 5 bytes which are allocated, the first 2 bytes must be read as in a single entity. Okay, so I'm storing right now 0 inside it. Then the third byte should be read as in a single entity. Only the third byte, 1 byte only represents one entity. So here we are storing A. And again, the fourth and fifth byte is again representing one single entity. Right now, we are storing 0 inside it. So this is how programmer is telling the computer that, okay, from the 5 bytes which have been allocated to the program, first 2 bytes must be used to represent 0. The third byte must be used to represent a character. And the, again, fourth and fifth byte must be used to represent a variable called as I. Right. So how the computer understands that, okay, first 2 bytes are clubbed together, the third byte is a standalone byte, and the fourth and fifth byte is again clubbed together. It understands because of the data type. So when we say int, we are telling the system that I want to access 2 bytes as in a single unit. So whenever we are specifying int k, indirectly we are telling the system that I want to access this first 2 bytes as in a single unit. So it is boundary created by the user. I want to access this third byte as in a single unit. I want to access the fourth and fifth byte as in a single unit. So programmer is creating a boundary on the computer's memory. So and what is the important part? Computer have a freedom to travel to each byte individually. So computer can go to the first byte, second byte, third byte, fourth byte, and fifth byte one by one if the computer wishes to do so. If computer is willing to do so, nobody can stop him, right? But as a programmer, you are like it's like we are making a request that please treat first 2 bytes as one type of a data, then the third byte as in a standalone, and then the again fourth and fifth unit as in a single entity. And computer is replying to your wish, and that's why we are able to use these blocks in the size of different data. Okay, any doubt in this? Any doubt in this? Great. Sir, if suppose we have a variable required, okay, there is a doubt. Let me open up the chat window. Oh. Jatin, sir, last program, but you had wrote int I, so I was telling that it should be int I. Okay, fine. Shreyas, if suppose if suppose a variable requires 1 byte to store, but in memory there is no 1 byte, instead there are 2 byte space. Shreyas, can you please elaborate more on the question?
Hello, sir.
Yes.
Sir, if in a memory, if a variable requires 1 byte space,
Hmm.
okay, and if there is no 1 byte, instead of there are uh, more than 1 byte space.
Okay.
So म्हणजे सर तिथे जर समजा 1 बाईट आपल्याला रिक्वायर असली आणि समजा तिथं मेमरी स्पेस मध्ये 1 बाईट नसली आणि 2 बाईट्स असल्या, तर मग तिथं जर आपण व्हेरिएबल स्टोअर केलं तर एक स्पेस हे जाणार ना, वेस्ट जाणार ना 1 बाईटची.
जर तू रिझर्व केला असलास, if you have reserved that much memory, then obviously it's a waste because it's like an array, na? So if I say integer ARR of 5, and if I just need only first location, if I am saying ARR of 0 is equal to 1, so I have reserved 10 bytes here, right? By assuming that int is taking 2 bytes, what I am saying is array ARR have reserved 10 bytes, right? But out of 10 bytes, I'm using only first 2 bytes. So I'm really wasting the rest of the 8 bytes. So that is true. That is what we were saying. Because right now I need only 2 bytes to store this, but still I'm at the wastage of 8 bytes. And correct me if I'm wrong. What I've understood is you are saying that in the computer there are these many bytes available, but your program needs only 1 byte. So what will happen, right?
Yes, sir.
So computer will use only 1 byte. It will ignore about the rest of the 4 bytes. Why it will allocate 4 bytes? It will never. Unless and until the programmer is not telling the computer to reserve the memory, the computer will not reserve the memory. So in the program like this, if you tell the computer that you want 10 bytes, and if you use 1 byte, then that's a sheer waste of the memory because you are reserving 10 bytes and you are using only 2 bytes. But if you tell the system that I need only 2 bytes, I don't want 4 bytes, I don't want 10 bytes, I want only 2 bytes. Now, in this case, even if there are these many blocks available, as you need only 2 bytes for storing this variable L, the computer will reserve only 2 bytes. It will ignore the remaining bytes from the memory. That is how it will work. Have I answered your doubt, or is there any other doubt? Okay. So guys, computer will reserve memory only if you tell the computer to reserve the memory. Computer will not reserve the memory ad hocly, right? So obviously, while reserving the memory, you must tell the computer how much memory you want to reserve. And uh, let's say you reserved 1,000 blocks, and you haven't used any block. So that is literally the wastage of 1,000 blocks. If you tell the computer that I need 2 blocks, and if you try to use 5 blocks, that's an overflow of 3 blocks because you told the computer that you will be needing only 2 blocks, and at actual you are trying to use 5 blocks. So you are overflowing the memory requirement by 3 blocks. So I am using even the broader term here called as a block. Okay. Any other doubt? Any other doubt? Shall we proceed?
Hello, sir.
Yes.
Sir, does a computer always use continuous memory locations to store different data types?
Yes, mostly. Unless and until you are not jumping between the functions, computer will be using a continuous space for storing the variables. It's called as in a stack. So every program is been allocated with the stack, and there are two types of stack every program runs in. For example, this is a main function, and if I create one more function called as data, right? And if I call this data function, let's say put a printf statement and do nothing inside it, let's say hello, it's just saying hello. And if I call this data in the from the main method, so there will be three. I hope you are attending, everyone. So this is a very important part. So in this case, program is creating a stack called as a program stack. So on the program stack, it will keep track of which function is executing. So initially, it will say that main function is on the program stack, and every function have its own variable stack. So now we are talking about two stacks at the same time. One for the method, which method is in charge. So on the program stack, you have called something called as a main. And in the main method, you need these many variables. So again, the computer will create another stack called as variable stack for main method. And on that variable stack of main method, it will create these many variables. Then in the main method, you are calling a function called as data. So what will happen is on the program stack, the main method is there. On the top of the main method, the program will queue data function. And in the data function, let's say if I have declared one more variable, integer a. So now this integer a has to be allocated a memory. Now this memory will be allocated on a different stack called as a variable stack for data. Now we are talking about program stack, the one which is keeping the track of which function is executing, the variable stack of main, wherein all the variables for the main method are being stored, and then the variable stack for data, on which all the variables of data method is stored or data function are stored. So these three stacks are coming in picture. So you will understand about how stack functions in the second unit. Till the time you can assume that for every function there is a variable stack, and this stack memory is a continuous memory. Stack memory is a continuous memory. Have I answered? Who asked this question?
Yes, sir. Got it. Thank you.
Who is this?
Ashish.
Ashish. Okay. Now, I really don't want to confuse you people, because as you explore more into the computer science, you will find that the memory that we are dealing with is called as a virtual memory. For programmer, virtual memory is continuous, and for the C also, virtual memory is continuous. So every program always assumes, or what is it, illusions, that memory is starting at the highest address and going to the 0th address. So every system thinks that entire computer's memory is allocated to me, and I have a freedom to work as if I am the boss, right? But in reality, that is not the case. There are programs called as schedulers, there are programs called as memory managers, which are who are taking care of actually finding free blocks from the RAM and allocating it to the program and taking it back whenever the programmer don't need it. So you will understand about this concept in more details as you proceed in the journey of computer science. It's a very beautiful theory that and practical, of course, that how these things work together hand in hand to allow multiple programs to work at the same time, parallel computing and parallel programming. It's a really nice theory. Okay, so till the time comes, you really understand what is the difference in a virtual memory and the actual memory of a computer. Probably you will start getting this concept. Firstly, you will encounter this theory in the DLDM, which you are already studying. Then you will encounter this theory into the COA. It is in the second semester, and then you will understand it pretty much clear into the two subjects called as operating system 1 in the third year first semester, and operating system 2 third year second semester. By the end of the operating system 2, that is third semester second third year second semester, you will be in exact understanding of how really the computer works behind the scene and how the memory management really happens. Till that time, you will understand that okay, this is a virtual memory, but it is a continuous block of memory. Are we sure? Shall we proceed? Okay. Okay. So whenever we are printing the address, okay, so let me print this. So what I can do is integer I is equal to 1 and printf %d and % of I. So if we are printing I, value of I, and file and run. So whatever we are seeing here, the address, it should print the address from my computer's memory. So this is not the real address. This is not the real address. This is address in terms of C environment, right? So it's a virtual address, virtual memory address created by the system to give me feel that I really have access to the computer's real addressing scheme. But that is this is the virtual address. But still, using this virtual address, I can do a lot of things, and I can manage the computer's memory, right? But in reality, this is just a virtual address generated by the system to show me. In reality, the computer is handling all the memory blocks on its own, and the operating system, like in my case, right now I'm using the Windows operating system. The Windows operating system is taking care of handling the real memory. Okay, so shall we proceed? Okay, so let's say I have int k is equal to 1, character c is equal to a, and integer j is equal to 1. I have error here. So how much blocks are required? By assuming that, how much bytes are required with the assumption that I am using 2 bytes for the integer. I need, how many bytes I need? Anyone? How many bytes are required by this particular program? Anyone? Yeah, of course, 5 bytes are required, right, guys? Yes. Now, if this is what we understand, that computer needs 5 bytes, and if we understand that malloc is reserving 5 bytes, so I can simply type here 5. So if we assume that integer is taking 5 bytes, these two statements are same. Like here also I am reserving 5 bytes, and memory alloc function is reserving 5 bytes. So memory alloc function, if I pass here 1, it means that you want to reserve 1 byte. If you pass here 2, it means that you want to reserve 2 bytes. If I am passing 5, it means that I want to reserve 5 bytes of locations. So whatever memory reserved by the above 3 lines and the memory reserved by this malloc function is same. There will be no difference in memory reservation, right? So before proceeding with this, there is a function called as size of a data type. So we'll try to use that to really see what is the size of a integer variable. So for integer, I'll be having 4-byte requirement, right? So not size of 3, I'll type int data type. And let me put a comment on this line till the moment. So, and printf, let's say %c, %d, comma, size of char. Okay, and size of, so this is how I can check out what is the size requirement for a particular data type. So when I'm saying size of int, the C environment will tell me that how many bytes are required to store one int variable. So guys, this program, there is no standard output. This program is going to change its output depending on the operating system, depending on the hardware of a computer, right? So let's say you have a pretty old hardware with you, you will get some different output. Let's say I have right now a new hardware with me, but I do installed a pretty old operating system, which is possible. I can install older versions of the OS on my this computer. So if I do that, again the output will change. Right now I have a latest OS environment and the hardware environment with me, so output will be different. So this program really do not have exact what we can say understanding of how much what will be the output. Nobody can guarantee it. It depends on which computer you are going to run, right? So if I compile this, hopefully it compiled. Yeah, warning, 3 warnings that I'm not using these 3 variables. That's fine. Let's run. Okay, I've made one problem. I'll stop it. Problem is I should put a slash n after printing the first output. Otherwise, I'll not be able to get exact result. So you can see that first output is for the integer. It says that I need 4. But by the way, this 4 is number of bytes. Okay, so I need 4 bytes. And for the character, it says that I need 1 byte. So in reality, my computer, how many bytes I've created? I have created 2 integers. For one integer, the computer needs 4 bytes. For one integer, computer needs 4 bytes. And for one character, computer needs 1 byte. So if I ask you how much memory is required by my computer, now it's a very specific question. How much memory is required by my computer? Obviously, the answer is 9. 4 plus 1 plus 4. So total 9 bytes are required. Exactly. Correct? Sorry. So guys, what I have to do is I have to say mlog 9. Mlog 9. Okay. And computer will reserve 9 bytes of blocks for me. So I'll be reserving 9 blocks of memory with me. But now we have understood that to store one character, I need 1 byte. So with 9 bytes, how many characters I can store? How many characters we can store with 1 byte? Sorry, 9 bytes. 9 characters, right? So it's not a rocket science question at all, right? So let's play with the pointers now. Let's play with the pointers, and we will tell the computer that what we want to store in which byte, right? So it will be a bit tedious to understand. If you are getting confused at any place, please let me know. We will take it slow. Okay, so what I'll do is I'll just remove this, and we will focus on these 2 data types because we know exactly how much bytes are required right now. For int, I need 4 bytes. For character, I need 1 byte. So we know exactly how many bytes are required. So we will focus on this. So what I'm doing is I'm saying malloc, let's say 4 plus 1, 5 bytes. So I'm again reserving 5 blocks of memory with me to store one more character and to store one integer and one character, let's say, or 5 characters. Obviously, I won't be able to store 2 integers because that is I am short of memory because I'm reserving 5 bytes, and to store 2 integers, I'll be needing 8 bytes of memory, right? So I'll not be able to store 2 integers, but I'll be able to store 5 characters or one integer and one character. That is possible. So let's what memory alloc function does is what is does is memory alloc functions. Let me take a clean slate. What malloc function does is, let me see. So there are some, let's assume that there are some blocks of memory, right? And we are calling malloc, let's say 5. So what this function does is this function goes to the computer, and each of this location will have its address, right? 000, let's say. Then we have 001, let's say. Then we have 002, and so on, up to whatever addresses we have, right? So these are the addresses that we have. Now, what malloc will do is malloc will go to the computer's memory and will reserve 5 bytes. So it will say I need first byte, I need second byte, I need third, fourth, and fifth byte. So I need this 5 bytes. And it has to return the address of where to start, but it will not return address of all 5 blocks. It will reserve the memory in a sequential manner, in the theory, of course, as I said. It will reserve the memory in the theoretical manner as in a continuous block. It will reserve the continuous block of a memory starting at 000 up to 004, and it will return the starting address. So it will say that all the 5 blocks are reserved at address 000. So what malloc is doing is malloc reserving 5 bytes and returning the start address where the first byte starts. The first byte starts at the 000. So it returns the starting address. So we are returning the starting address of a memory where we are reserving. Now we know that 5 blocks have been reserved. Now what I'll do is, now we know that malloc is returning a address. So address means what? Address means pointer. Pointers are used to store the addresses. Let me use character pointer, character star, let's say memory. Character star memory. So malloc is returning a pointer, and I'm returning an address, and I'm using a pointer variable to store the address. Obviously, that is correct because pointer variables are designed to store address. Sure, but there is one issue. We tell the computer that these are the 5 blocks, like integer k and character c. So the 5 blocks have been reserved for this too also. So we have already told the computer that the first 4 bytes will be used to store an integer, and the last byte out of 5 will be used to store a character. In this case, we are not telling anything like this, right? So there is one problem. If I compile it, let's see whether the compiler complains about it or not. So compiler has not complained about it. Okay, fine. Ideally, I was expecting a complaint because it's a plain memory. Now what I can do is it's guys, now these two lines will be similar. Character, let's say store of 5. Now these two lines are similar ones. Like you are creating array of size 5 and you are reserving the memory of size 5, and you will be able to store 5 characters in using each memory. Are you with me? Are you with me? Okay. So let's try to use like character store. You know how to store characters inside it, right? So let's try to use this character pointer to store character values, right? So what I can do is star main of 0, or not even that directly. The array is equal to 0 and a. Oh, ho, ho, ho. Control C. 1, 2, 3, 4, 5. Yes. 1, 2, 3, 4. And A, B, C, D, E. Okay. And or let's simply say printf %s, comma, memory. Let me use star memory is equal to let's see what happens. Can you see ABCDE? Can you see ABCDE on the screen? Yes. So now who decided how to use this memory? It's us. It's us, the programmer decided how to use this memory. Now let's tweak it. Let's tweak it in the way that we will store 1 byte and 1 character. We will store 1 byte and 1 character. Oh, sorry, not 1 byte. We will store 1 integer and 1 character. Okay, like integer k is equal to 1 and character c is equal to a. In the same way, we'll try to store 1 number and 1 character using these 5 blocks which are freshly allocated. Okay, so right now I've stored ABCD. So what I'll do is, for understanding purpose, I'll just put this everything inside the comment. But now we have just understood that okay, you can do it. So let me put a comment. Okay, now I have a starting address, right? I have a starting address. Now if I want to store a number, if I want to store a number in the 4 blocks, out of this 5 blocks which have been allocated, I need 4 blocks to store a number. So there are multiple ways in which I can do it. There are obviously you can do it in a really different ways. What is a simple way to do it is you will simply write star mem is equal to k, and let's say memory of the last index will be 014 is equal to, sorry, will be a, then printf. It will be a very tricky job. It will be a very tricky job to print this everything because we are messing up with the memory. We are storing an integer and a character. So what I have to do is I have to read first of all only 4 bytes out of it, and then I have to try to print the last byte. So that will be a really tedious job. So before printing it, I'll just try to print the last bit out of it. So memory of 4. So let's see whether we have stored it or not. Okay. Okay. Have printed? Yes, I've printed A. So can you see A has been stored in the last location? Okay. Great. And now the trickier part, printf %d star mem. Okay. It will create a problem, I guess, because it's a character pointer, and I'm trying to print. I just want this will print only 1 byte because it's a character pointer. So what I'll do is I'll create a integer pointer p, and then I'll say p is equal to. And right now, see, I've created an integer pointer called as p, and then I'll say p is equal to memory. So now p and memory, both things are pointing to same memory. So instead of using mem here, I'll use p. So what is happening is, as my pointer is of type int, it knows that if somebody is going to access a memory, it needs to read 4 bytes from the system. Now here I'll say this is first 4 blocks of mem from system is equal to, okay, and let's compile. Let's run this. Can you see the output? Okay, I've printed the address. Let's print the value is equal to and then /n. The system is equal to A has been printed. This is the first 4 blocks from the memory, and I am getting a byte data because I'm trying to convert it into the address. So I need to handle it in a bit different way, I guess. P is equal to memory. So I'll get the address. Somehow to do it. I guess I've messed up in this case. In this case, I've messed up. So memory 1 to 8. So I should go like this. So this will be integer blocks now. This will be the integer blocks. Earlier it was a character block. So in the case of character block, I need to go to the last part. So obviously 0, 1, 2, 3, 5, 4, that was correct. And if I have converted it into the integer memory, integer pointer, then if I assign the memory block, if I get the address, then just simply try to print using the star p.
So at
Okay.
so at line
Hmm.
number 10, what if you write mem is equal to ampersand of k? I mean address of k.
Yeah, that's fine, I guess. I don't want to go to the void pointer. You are leading me to the void pointer concept. This will go in kind of a void pointer concept. So have I stored one? Yeah, I've stored one, right? So I guess this was the error, right? I was using star and this should work also. Yeah. So the error was in here, this statement. I was using star mem. In the pointer, I was keeping the address and it was printing the correct result. So I should have got it at the first place itself. Now this extra study is not required, whatever I've done. Whatever I've done here, it's not required. It is just the additional stuff that I entered because of my simple silly mistake. Now what I can do is I can simply print P here. Thank you. Who was this? Who was this?
Sir, me Ashish.
Ashish. Thank you, Ashish. So it was a blunder. So now if I run, I'll get one on the screen. So see guys, what we are doing is we are reserving 5 blocks, and out of these 5 blocks, first 4 blocks I've used for storing the integer, and the last block I used it to store a character variable, and it works fine. Is it okay? Is it okay? Yeah, great. So please forget about whatever I've typed to because of just small mistake that I used. I used something called as a void. I really don't want to drag into the void concept immediately. It's a pointer which can point to hell anything, and it really do not have any space limitation. Like character memory always goes with 1 byte. Integer pointer always goes with the 4 bytes. The void pointer, we can tell him how many bytes the void pointer should travel. So because of the mistake that what I wrote here is that was a really blunder thing. I said character star mem and ampersand k or the k. It really created a problem for me while dealing with the program. So I should have pointed to address using address rather than pointing a value to the value. So this is a blunder that I created because mem was an mem is. So it really means I am accessing this star mem really means that I am accessing 1 byte and I tried to store 4 bytes and it resulted into an error. So this statement, what is the problem with this statement? I should have got it that star mem means that you are trying to read 1 byte and k is trying to send 4 bytes and this statement created a problem. So instead of that, uh, what we should do is main address of key shall be copied inside main. Okay, that is the base thing. So please forget about this. And I guess you really know already what is the meaning of this. This is the base address plus the first location, right? We have seen this formula earlier. pointer plus base address. Yeah, so this concept is clear to you. So I really drained into this concept without necessary. Okay, so P. And let's run this one more time for our satisfaction that it's working. Okay, I've created here P. Yeah, fine. So let's compile, let's run, and we should see A and 1 on the screen. So guys, it's up to us how really we want to represent this memory. And like this blunder that I created, character memory, wanting to read only 1 byte and assigning it 4 bytes, assigning a memory, that creates a hell lot of a problem. And it may happen a lot of time in the C. So dealing with the memory is very crucial job. But there is one bad thing is about this program. The bad thing is uh, whenever we reserve a memory using integer and character in this plain way, this memory is getting allocated on a stack memory, and there is also something called as a heap memory area, wherein this malloc is reserving the memory. So these two memory areas are different. Malloc memory area is a different than this integer k and character c memory area. The memory management rules never change. Whether the memory is from the stack area or the memory is from the heap area, the memory management rules will remain same. How you can deal with the memory, that really do not change. Like we can overflow from k to c. But what happens to the releasing of the memory? So when this program terminates, now I've already executed this program couple of times. So let's say one time, second. This is the second time I'm running. This is the third time I'm running. So there is one problem happening in the background, right? So what is the problem? Problem is every time the program terminates, the stack created for main gets destroyed. So the variables which are on the stack of a main method. So let me come here and let's understand what is the problem with this approach. So first thing, it will really solve our requirement problem. So in the runtime of a program, if let's say I need 6 blocks, then I can reserve, instead of saying 5, I can reserve 6 blocks. So in the runtime of a program, you can decide how much memory is required by you. But what is the problem in this case is, let's say this is the variable stack which is created. In here we have k and here we have c. So these are 3 variables, and here also we have a pointer called as main. So this is a pointer. But in reality, this malloc reserves a memory on something called as a heap area. So there is a memory space called as a heap area, right? So there is a memory called as heap area, and this memory is totally different. So what happened is, on this heap memory, 5 blocks of memory has been reserved. 1, 2, 3, 4, 5. And the address of this 5 blocks was returned to the program. Okay, so this happened for the first time. When I run this program for the second time, that means program terminated. So as soon as the program terminated, this stack got destroyed. This stack got destroyed, but the heap remains in the memory. Heap remains in the memory. So these 5 bytes which have been allocated are not released by the computer. These 5 bytes are still there, but the stack got destroyed. And when the stack got destroyed, the memory allocated for K and memory allocated for C also got destroyed. So the memories have become free as soon as the program terminates. Now, when I run the program for the very next time, what will happen is, uh, when I run the program for the next time, a new memory will be, memory stack will come in picture. Okay, so the earlier stack has been destroyed, and now as you are running the program for the next time, what we are doing is we are again allocating a stack memory, and again we are saying that I have key. This is happening for the second time. Then you are saying C, then you are saying I need a memory pointer, and this memory pointer needs to reserve a memory. So the computer goes to the heap. It says, okay, I need to reserve 5 bytes. I need to reserve 5 bytes. I need to reserve 5 bytes, and then let's say this is 001. Then it returns this 001. Okay, and the 5 bytes have been available. Now again the program terminates. The second time program has executed, the program terminated. Okay, so program executed, program terminated. Now I'm running the program for the third time. When I run the program for the third time, let's say the program is running for the third time, again the similar story will get played. You reserve K, you reserve C, you say I need a memory, and computer goes to the heap and it reserves the memory. It reserves the memory. Okay, 5 bytes are reserved. Let's say it starts at 002. Then this address is returned. Again, the program terminates. So K is destroyed, memory pointer is destroyed, but the heap memory is still there. So you people got the problem, right? So you know what is the problem now. Can anyone tell me what is the problem in this approach? The second approach that we are doing? Can anyone tell me what is the problem in the second approach that we are applying for the memory? Anyone? Anyone? Or shall I explain again? May I need to explain again? Shall we repeat? I need some feedbacks. Can anybody tell me? Yes. Sir. So, okay. Sorry. So let's repeat. So this time even bit slow. So whenever we have main method, computer always allocates a memory. So when main method starts execution, computer allocates a memory. Huh. So for the variables of type int, character and all, let's put it on the left side of the window. So whenever this KC is created, the computer reserves a memory on the stack. So let's say this is the stack memory. There are two types of memories in the computer, stack memory and heap memory. Okay. On the stack, we keep all the variables which are in scope. So K is in scope, variable C is in scope, and memory is in scope. But what is a mem? Mem is a pointer, right? So means it's keeping the address of some memory in the system. It is keeping the address of some memory in the system. So it's not really a variable. It is just a pointer to some memory. So it is pointing to some memory. And what we are doing is saying we are executing a statement called as mlock. So this mlock, what it does is there is a tree in the system. That tree is called as a heap. There is a tree in the system. This tree is called as a heap tree. This is a completely different memory management mechanism of operating system. So this stack and this heap is been managed by the operating system of your computer. Let's say this is managed by the OS. It's OS who is managing this memory. So whenever we say int k character C, that time OS allocates memory on a stack. Or whenever I say char star mem, the variable is created on a stack. Whenever I say mlock, the OS allocates a memory on heap. So this is a separate memory location. The OS will allocate a memory on this heap area. So let's say 1, 2, 3, 4, and 5. 5 bytes allocated. So let's say this address is 000. So what OS does is it reserves the memory 5 bytes using the mlock, and then it returns the start address of this memory, and it is copied inside mem. Okay. Now the program terminated. So as soon as the program terminates, what OS does is OS deletes this stack. So memory has been free. So this pointer is also been deleted. But look at what OS is doing. OS is not deleting the memory on the heap. It is keeping that memory, right? So OS never deletes the memory on the heap unless and until it is instructed to do so. So we have to tell the system that you must delete a memory from the heap. So whatever we have allocated on the heap, the 5 bytes are still there. Now, when you run the program for the second time, again OS allocates a stack. Again, OS creates a stack. And in the stack, again, it allocates the memory for K, it allocates the memory for C, it creates a pointer variable called as mem, and then mem says that I need a memory of 5 bytes. So OS reserves 5 bytes. So you have 5 bytes with you now, new 5 bytes. Let's say its address is 001. So this address has been returned, and this mem now points to 001, a new address. Now this 001 is pointing to the freshly allocated memory. Again, the program terminates. What OS will do? It will remove the stack, but the heap will be there. So now you got the problem. What is the problem with this particular approach, mlock approach? Can anybody tell me what you really got? What is the problem with this approach? Can anybody tell me what is the approach? Space complexity. Yes, guys, that is really nice word that used. That is used. That is space complexity. So I was expecting only the memory wastage or a space wastage, but complexity is even nice word. So we are wasting memory. We are wasting memory, right? So let's say if I write here, right now I'm using 5 bytes. So everybody, everyone from you batch, what you can do is you type here or whatever number you want, right? These many bytes you want to reserve and run this program in a infinite loop. Run this program in a infinite loop. What it means that reserve the memory, reserve the memory. You will be keeping reserving the memory continuously, and as this memory is not been released unless and until you are telling the system to do so, it will just keep on reserving the memory, and your hardware of a computer soon will reach the point wherein there is no more memory available to reservation. Your computer will soon hang, will stop responding because of a lack of a memory, and you have to take a hard reboot or a reboot the program. So that is the problem with this thing. It needs to be handled with very care. Okay. So is the concept clear that yes. So if you want to explore, if you want to just experiment with this, try this program. Now that modern operating system, what they do is, as soon as they see a program is going to end up in messing up with the entire environment, sometimes the OS interrupts that program because there is a concept called as a high priority program in the OS. High priority programs which have a capability to terminate any other program from the system. So because of that high capability programs or the high priority programs, what happens is OS ultimately terminates the program called as this one is called as mem2.c. So this program will be terminated by the OS as soon as it understands that okay, this program is eating up a lot of memory, causing the other system programs to malfunction, and the system will kick in and it will show a message that oh, you can't run this program henceforth, or no longer this program can be supported because so and so reason, and the system will interrupt the program. But if you find some old systems, or if you find some Linux based system wherein there is a still allowed execution for infinite memory allocation, you will definitely end up into the system which will hang, okay, and the computer will definitely stop responding. So I recommend try to execute this with the care that you have already saved all the data, you have saved all the files, and for the sake of fun, you are executing this program. And definitely, maybe 70-80% of the time you have to reboot the system in turn to make it accessible again. And 20-30 times the task manager or the memory manager will kick in and it will save you from being from the need of being restarted. Okay, so just do it for the fun purpose, right? Now, how should we deal with this? So as soon as our job is done, so here, as soon as our job is done, what we should do is we should say free and then pass the pointer, which is pointing to the memory, free mem. So what this line means is, this line means as soon as the program terminates, go to the heap and release the memory. Go to the heap and release the memory. So as soon as we use free function, the program will go to the heap and will release whatever the memory has been allocated to the program. So the programmer has to explicitly free the memory allocated using malloc function. Now the program won't run into the hang situation, or program won't run into the lack of memory situation or unstable situation. Program will make sure that as soon as the job of the memory has been done, it will free all the memory which has been reserved. Is the concept clear? Yes. Okay. Now, what is the relation of this particular memory allocation with the program that we have seen for the structure, for example? What is how we can relate it to the structure? So let me see, don't save, and so how come it is related to the structure? What I can do is, what I can do here is, let's say I know clearly, let me remove the rest of the things from this program. We just simply delete this. let's say I am well in advance in the knowledge that I need a memory for storing a integer. Now, this integer is of different size on the different system. For on one system it is of 2 bytes, on one system it is of 4 bytes. So how to write a program which will run? Now, if let's say I know that my computer takes 2 bytes, I'll say 2. If I know that my computer needs 4 bytes, I'll say 4. But how to write a program which will reserve the memory despite of the hardware or despite of the operating system, the program must work fine. Doesn't matter on which hardware, which operating system the program is going to execute. If we need a memory to reserve an integer or to store an integer, it must allocate the memory which is required to store the integer. So for that purpose, we can use size of function, size of operator, and I should write here size of, not main, I should write int. So what it tells the computer that you need to reserve the memory size of operator integer. So what this will do is it will bring or it will pass the size of integer to malloc. So if my system needs 4 bytes, it will pass 4 bytes to the malloc. If my system needs 2 bytes, it will say 2 bytes to the malloc. And then we are pointing to the memory using integer pointer. Sorry. Okay. Now let's say if I need array of size 5, if I need array of size 5, I can simply reserve the array of size 5 like this. In the similar way, if I need malloc function to reserve the memory for me, what I can do is size of int. So if my integer needs 2 bytes, sorry for that, if my integer needs 2 bytes, 2 into 5, I'll be needing 10 bytes. So that's what I'm doing here. I need to store 5 integers. So 5 integers array means you are storing actually 10 bytes. If my system is requiring 4 bytes, when I say I need to store 5 integers, I am actually storing 20 bytes. So what will happen, this malloc function size of int will return 4 into 5, 20. So 20 bytes will be returned. So now you are understanding these two statements are equal. Are you with me? These both statements here, that reserving the array and the malloc function that I'm writing, both are equal. Really nice. Great, great. And now with the structure struct student, it was a structure that we created, right? If I say int I, or let's say int roll number and character name, let's say it was array of size 30. This is what we are using. Now if we print, if we simply go to the printf and let's say %d size of s. Now you know that I'm going to create a variable of student struct student, and I'll say it as s. Now here I should say the total memory required by student is equal to, okay, and hopefully there is no other printf statement, so this is the only thing which will print. The total memory required by student is 36. Yes, are you with me? Okay. So this is how we can work with it. This is how we can work with it. Now, if I need to store one object, if I want to store one object of a structure, what I can do is struct student. That this is how I want to read my memory in the terms of structure. And malloc size of struct student. So it will allocate a memory to reserve, to store one object. It will allocate a memory to store one student. I need to store 10 students. Now it will allocate memory to store 10 students. I need to store 100 students. Allocate the memory for 100 students. Are you with me? Let's say allocate 50. Yes. So now, sorry. So with this understanding, till now, what we are going to do is we are now going to shift into the discussion of data structures, that is stack, linked list, and queue, for better understanding of this. But I really recommend you people to explore this MLOC with the structure. By the way, I have to typecast it here. There is one concept of typecasting. So I should typecast this returned address into the struct student star. So what happened is this MLOC simply is returning the memory pointer, and my left side is requesting for the memory pointer of type struct student. So it returns a pointer in the memory, and the left side is in the pointer to the structure. So we have to typecast the memory pointer into the structure pointer. And how we are doing a typecast? We are simply passing in bracket struct student star. So this statement is required to typecast the memory pointer, blank memory pointer from the system into the category of struct student pointer. Okay, so that is how now this statement is going to reserve the memory, which will be able to store 50 students, 50 students record. It's as good as creating array of size 50. Okay. So let's stop here on the discussion of structures and the memory alloc. There is one more function called as calloc, but we will discuss the calloc in the when we start with the some concept called as linked list. That time I'll touch the concept of calloc function. It has a very unique syntactic style. It says now see you can see that malloc is taking one array, one argument, whereas the calloc needs two arguments. Okay. The first one is how many locations, and the second one is how many bytes. What is this how many locations and how many bytes? We will discuss in detail when we'll start with the linked list program. Till that point, we will come along with the MLOC kind of. Okay. So try to explore the concept of MLOC with the task of structure. So this is the task that everyone must try out. Now it's 10:30. We will take a break of only 5 minutes, and then you have a discussion among your groups. We will start taking review of our PBL activity. So it's 10:30, almost exactly at 10:35. We will resume our discussion. No need to leave the meeting. Let the meeting running and take a break of 5 minutes because it's almost 1.5 hours. We are continuously discussion. Let's take a break of 5 minutes, and immediately after 5 minutes, we will start discussion on PL activity. Any doubts? Let's take a quick break of 5 minutes.